Imagine a perfectly arranged array of atoms, a crystalline lattice, the very essence of order in the material world. Now, picture a tiny disruption in this otherwise flawless arrangement, a single atom out of place. This, my friends, is the essence of a defect in a crystal. One such defect, known as the Frenkel defect, occurs when an atom abandons its rightful position in the lattice and lodges itself in a nearby space, a sort of interstitial void. These defects, while seemingly insignificant, can have a profound impact on the properties of a material. They can influence its electrical conductivity, mechanical strength, and even its interaction with light. Understanding these defects is key to unlocking the potential of materials and tailoring them for specific applications. Now, let's delve deeper into the fascinating world of Frenkel defects, specifically those occurring in ionic solids. Ionic solids, as the name suggests, are composed of ions, atoms that have gained or lost electrons, and thus carry an electrical charge. These ions are held together by strong electrostatic forces, forming a tightly packed crystal lattice. It is within this lattice that the story of the Frenkel defect unfolds. In the tranquil world of a perfect ionic crystal, each ion occupies a specific position within the lattice, dictated by the charges and sizes of its neighbours. However, like all things in the universe, these crystals are subject to thermal fluctuations, those tiny jitters of energy that permeate all matter. Occasionally, an ion, usually a cation, a positively charged ion, gains enough energy from these thermal fluctuations to break free from its designated spot in the lattice. Now, instead of staying put, this energized ion finds itself drawn to a nearby interstitial site, a small, empty space between the regularly arranged ions. This movement creates a void at the ion's original location, a vacancy, and simultaneously, the ion becomes an interstitial atom, residing in a space not meant for it. One might think that such a relocation, an atom essentially playing hooky from its assigned position, would disrupt the balance of the crystal. However, the Frenkel defect is a remarkably balanced affair. While it does create a vacancy and an interstitial atom, it doesn't alter the overall composition of the crystal. The crystal's stoichiometry, the precise ratio of its constituent ions, remains unchanged. This is because the defect involves only the displacement of an ion, not its removal or the introduction of a foreign one. The same number of cations and anions remain, just slightly rearranged. Similarly, the density of the crystal remains largely unaffected. The displaced ion, though now in an interstitial site, is still very much part of the crystal and contributes to its overall mass and volume. The slight rearrangement caused by the Frenkel defect doesn't significantly alter the crystal's density. Section 4. Why cations are the usual suspects. Now, you might wonder, why cations? Why are they the ones more prone to these interstitial escapades? The answer lies in their size. Cations, having lost one or more electrons, are generally smaller than their anionic counterparts, which have gained electrons. This smaller size makes it easier for cations to squeeze into those tight interstitial spaces within the lattice. Imagine trying to fit a basketball into a box meant for a tennis ball. It's not going to happen. But trying to fit a tennis ball into a box meant for a baseball, while a bit snug, is more likely to succeed. Similarly, the smaller size of cations makes them more likely candidates for forming Frenkel defects. Section 5. Frenkel defects in action. Real-world examples. The world of materials science is replete with examples of Frenkel defects in action. Take, for instance, silver bromide, a compound used extensively in photographic film. The light-sensitive nature of silver bromide, its ability to capture images, is in part due to the presence of Frenkel defects. Another example is zinc sulfide, a compound used in luminous dials and X-ray screens. The luminescence of zinc sulfide, its ability to emit light, is influenced by the presence of Frenkel defects, which facilitate the movement of charge carriers within the material. These examples highlight the important role that Frenkel defects play in determining the properties and applications of materials. Section 6. The ripple effect. How Frenkel defects influence material properties. The presence of Frenkel defects, though seemingly a minor imperfection, can have a significant impact on the properties of a material. These defects can alter a material's electrical conductivity, its mechanical strength, and even its interaction with light. Think of it like this. The perfectly ordered lattice of a crystal is like a smooth highway, allowing for the easy flow of traffic. The introduction of a Frenkel defect is like placing a small obstacle on this highway. It disrupts the smooth flow, causing a detour, a change in the normal path. Similarly, in a crystal, the presence of a Frenkel defect can disrupt the normal flow of charge carriers, those tiny particles responsible for electrical conductivity. This disruption can either enhance or hinder the material's conductivity, depending on the specific material and the concentration of defects.